For people using finger prick tests, they may prick their fingers over 1,000 times a year. Each test means piercing skin and drawing blood. Then, they wait for the glucose number. The blood mark is not just a test spot, it is a daily mark of pain. Many patients face about 1,000 needle pricks each year, for hundreds of millions worldwide. This burden may last a lifetime. The red dots cross national borders, forming one huge global problem. Countless families face the same struggle. Must glucose monitoring always require blood? Materials scientists are exploring another way. This is not an ordinary patch. It combines microneedles, hydrogel, and sensors. It is a tiny skin laboratory. Without blood, how can it track glucose? The answer is interstitial fluid under the skin. Each microneedle is under 1 millimeter long. It does not aim for blood vessels, but for shallow interstitial fluids. Now, zoom in further. This is 1 microneedle passing through the skin surface. It reduces contact with blood vessels. It reaches the shallow fluid-rich region, as shown here. No blood contact, less deep nerve interference. This shows low invasive, low pain potential. The key is not a sharper needle, but a smarter material. It works like a signal window, reading glucose clues in interstitial fluid. When hydrogel microneedles touch interstitial fluid, their hydrophilic structure attracts water. At the microscale, polymer chains form a 3D network. This network draws fluid inside. As fluid enters, the polymer network gradually expands. The hydrogel swells like a sponge absorbing water. It keeps glucose-containing fluid inside. Specific functional groups in the hydrogel network can selectively recognize and bind glucose. After absorbing the fluid, how does it sense the glucose level? This is where the recognition groups become important. They work at the molecular scale. The yellow blocks are glucose molecules. They move into the sensing core, where glucose levels can be decoded. The key is phenylboronic acid groups. They bind to glucose cystiols. This forms a reversible bond. It is like a temporary lock at the molecular. After recognition, chemistry becomes an optical signal. Along the fluorescent pathway, energy transfer between fluorophores changes. The local changes from glucose recognition becomes a measurable fluorescent signal. In short, instruments can read it as light. Along this glowing blue chain, the reader captures the fluorescence change. It becomes a changing data graph. When blue light shines on the microneedle array, a wireless module can be added. It sends the sensing information to a smartphone. Through wireless transmission, polymer recognition and optical reading finally appears on the phone screen. Although this technology is exciting, it still faces 3 key challenges. First, time lag. The patch reads interstitial fluid, not blood, so patch readings and real blood glucose changes may have about a 15-minute delay. Second, biofouling. The human body is complex. Over time, proteins may attach to the sensor surface. This is called protein fouling. Third, long-term stability and clinical validation. As the fluctuating graphs show, stable signals may cause glucose reading errors. That is why scientists keep improving hydrogels, microneedle structures, and signal stability. One day, glucose checks may no longer need blood. That is the future we hope to see.
以上是高分子材料的故事，接下来是我的故事，准确来说，是我和 AI 雷包组员互相折磨的故事。期末时间不够，我以为 AI 可以救我，影片能一键生成，结果没有，完全没有。我说要医疗科技感，他给我科技晶片；我说要手指采血，他真的很努力，只是他坚持扎在指甲上，对，指甲，然后8秒额度用完后，最便宜还要$30。AI 还没让我毕业，先让我的钱包退学。最后，你知道谁在做吗 ？Paper 我查，脚本我写，素材我修。这部影片不是 AI 一键生成，是 AI 负责制造混乱，我负责把混乱剪成作业。 但也多亏它，我才有机会把脑中的想法一步步变成真正的画面。这次不只学到高分子，还解锁了全套剪辑技能。虽然过程很崩溃，但做出来后真的很有成就感。